everyone, and welcome to ChemSusChem's first virtual symposium. The topic of the day is lignin valorization. And as you all know, lignin has for decades been the most underused and undervalued component of biomass. And new strategies are required to improve its use in biorefineries. Now, this has prompted us at ChemSusChem to take a closer look at the state-of-the-art of lignin research, and that resulted in our recent special issue on lignin valorization from theory to practice. Now, today for this symposium, we have 4 of our wonderful contributors from the special issue: Katalin Barta, Hegg, Claudia Crestini, and Changzhi. And they have graciously agreed to give us a glimpse into their research on lignin valorization. Now, our presenter today is Joseph Samec, who is one of the guest editors of the special issue. And he obtained his PhD at Stockholm University and then went on to do a postdoc at Caltech with Professor Graz. He returned to Sweden to the University of Uppsala as an assistant professor and then returned to Stockholm University as a professor in 2015. Joseph's research interests are the sustainable chemistry for organic synthesis and lignin valorization. And he's also the co-founder of a startup company that produces biofuels from lignin. Now to the procedure. I can say that if you have any questions or issues during the presentations, you can simply use the chat function and I'll do my very best to help you out. We'll have some time after each talk for questions, so please put any questions you have for the speakers in the chat as well, and Joseph will then read them out after each talk. I'd ask you to begin your questions with @Katalin, @Eric, and so on, so that Joseph has an easier time sorting through them. Yeah, that's it from me, and I'll hand over to Joseph now, who will introduce our first speaker. Joseph?
Thank you, Andrea, and I also want to take the opportunity to thank the whole ChemSusChem editors for putting this symposium together. I think you have done a terrific job in being able to extract out these 4 very diverse and interesting talks that we will hear this morning in the Americas, this afternoon in Europe, and this evening in Asia. So I will go directly to a presentation of the first speaker, who is Professor Katalin Barta. So since this year, actually, Katalin Barta is a professor at the University of Graz in Austria.
Yes, it's working. Okay, thank you. Thank you.
Now Claudia came in too. Good. Okay, before this, she was a professor at the University of Groningen in the Netherlands. So the Barta group is focused on lignin valorization, catalytic fractionation, and the lignin first approaches, and she has actually developed her own unique protection group chemistry on the lignin valorization. But she's not only interested in the fractionation, she also takes these building blocks and produces new platform chemicals from these biomass-derived molecules. And she uses, of course, green and sustainable chemistry to do this. So I'm very honored to present the first speaker today, Professor Katalin Barta, on the topic lignin first, catalysis, platform chemicals, and valorization pathways. So please, Katalin, the screen is yours.
Thank you, Joseph. I hope now you can hear me at least. I will start sharing my screen. I think this should be fine. Now, hopefully you can see my slides. So is it okay? Please say if there is any issues with the presentation, because I can't see. Is it okay? Okay, fine. So
just click on the little box at the bottom.
Oh, yes.
Thank you.
Is it
Great.
okay? Yes. Okay. Thank you very much. A little technical difficulty here. And it's an honor to be presenting here. Oh, now it will be an update. I hope I don't blend out completely, but before I go completely blank, I would like to welcome you to this Lignin workshop, which is I think a really nice opportunity for us to come together and talk a little bit about recent, very exciting research in lignin valorization. So good morning, afternoon, and evening to every one of you. I would like to talk to you about lignin-first approaches today. And specifically, I would like to present two ChemSusChem papers that we have recently published in special issue of lignin valorization. One of them you see here is a mini review that actually was, this was led by Suha-san, who is actually my ex-PhD student, and now he's a professor in China. So this was actually collaboration with the Chinese team you see here. And this other paper is, as Joseph already mentioned, on some of our strategies that we have developed in lignin-first fractionation without metal. So this is a protection group chemistry in combination with lignin-first approaches. And I just would like to present you this Groningen dream team of lignin valorization. Peter Dawes, he has his own group, very successful. Two excellent postdocs, Maxim Galkin and Kieran Laiv. If you want to know anything about lignin and lignocellulose, contact them. And a very talented PhD student, she's just finishing in my group, and I believe she will be looking for jobs soon. So Ale De Santi is just going to defend her thesis in my group. So this is the work I would like to present to you today. And I would like to start with actually discussing a little bit, refreshing what lignin-first actually means. So here, what we are talking about is an umbrella term, essentially, regarding preservation of the quality of the lignin as well as the polysaccharides. It should be considered upfront in a biorefinery setting. This means that if you compare a lignin-first strategy to a classical strategy, which is shown here, lignocellulose would normally undergo some harsh processing conditions with the goal to get high-quality cellulose out. In this case, the lignin constituent would actually be left behind as a low quality, a highly modified lignin. So even though you can try to utilize this lignin, it will not be so easy to do so. So in a lignin-first setting, however, what we aim for is preservation of the quality of both the lignin as well as the cellulose fraction, which increases atom efficiency. Briefly, what it is lignin is liberated from the lignocellulose matrix by usually solvolysis, with a solvolytic method, and then there is some kind of stabilization also involved. I will come back to this point, what this might be, and it might be also combined with the depolymerization processes, essentially to deliver, in this case, is a reductive catalytic fractionation to deliver very high yield for aromatic monomers. So to compare, such aromatic monomer yield will be significantly higher than the one that would be obtained from such a lignin that is highly condensed. So this would be, in a nutshell, a lignin-first approach. I would like to also point your attention to this review perspective. It's a very big collaborative effort, actually, led by Joseph Samec, our moderator today in Energy Environmental Science, which basically presents the guidelines for such a lignin-first biorefining. Just to come back to what is the chemistry behind some of these processes, I would like to also show you this scheme here, which would be essentially the behavior of a beta-O4 lignin unit under solvolytic / acidolytic conditions. So basically, if we have this beta-O4 unit, this alpha position is relatively labile. It will, especially in the presence of even small amount of acid, would dehydrate to create these benzylium ions, benzylic carbonium ions, which are relatively stable. You can see also the tautomeric form here. And this carbocation, benzylic carbocations, would actually be sort of capturing nucleophiles that are around. So it could be an intermolecular or intramolecular capture, for example, by another lignin moiety that is around. That would actually result in the formation of these recalcitrant carbon-carbon bonds you see here. So such moieties would represent the modified lignin, essentially, for example, in after pulping of organosolv pulping. So this is a natural process that is ongoing under solvolytic conditions in a lignin. And here in this perspective, we have I just took it from as a quote from this paper. We define lignin first as an active stabilization approach that liberates lignin from the plant cell wall and prevents condensation reactions. So the question is, how do we interfere with this natural tendency of lignin to form such condensed moieties? And there are many ways, if you look at the scheme, to actually do it. So there is some problem with my PowerPoint. One possibility that we have to consider under solvolytic conditions, and this of course depends on temperature and processing conditions, but basically not only there is condensation, but there is also solvolysis ongoing to produce some monomeric fragments, which would look like this, which are reactive. So these would also undergo condensation processes. However, if we invoke, let's say, hydrogenation in the presence of a metal catalyst, and this is one of the most common lignin-first approaches to date, that would actually hydrogenate such unsaturated fragments that we could actually get to reduced monomers, which would be stabilized. Stabilization also considers these fragments here, and these could be oligomeric fragment. Sorry, there is really something wrong here. For example, the hydride can actually be the nucleophile. So in this case, there will be also hydrogenolysis pathway, also stabilizing such reactive fragments, oligomeric fragments, to get again to reduce monomers. So this is the reductive catalytic fractionation setting that we are talking about, one way of stabilization. The other way of stabilization post-depolymerization would be this pathway here, which is essentially a cleavage pathway under more acidic conditions. So this is an acidolysis pathway that starts from these intermediates and results in the formation of the C2 aldehydes, which are reactive. These also undergo condensation processes. So these guys and these guys actually go to additional condensation pathways, which we have also demonstrated by several spectroscopic methods. However, if we now protect these aldehydes in the form of cyclic acetals, for example, by functionalization with thiols, then you can get again some more stable monomers. So these processes, stabilization approaches, would be actually via or during depolymerization methods. And there are some which can actually be invoked prior to depolymerization, and that is these strategies here. So this is the Jeremy Lutherbacher's group chemistry, which is a very nice strategy. This is the essentially capturing of the beta-O4 moiety in the form of a cyclic acetal. Here is acetal formation again, but here lignin diol moiety is being involved in the cyclic acetal formation with a suitable carbonyl compound. So this is kind of like locking the lignin in its native structure, and it's possible to isolate these. And the other possibility would be the Stahl-Westwood chemistry, where selective oxidation of this benzylic position would result in this carbonyl compound, which will no longer dehydrate. Both of these are, as you see, prior to depolymerization, but they can be subjected to reductive treatment and then again get higher monomer yields, because simply the beta-O4 content in these stabilized lignins would be much higher. Another stabilization way would also be that an alcohol acts as a nucleophile here and essentially protecting this benzylic position in the form of with some kind of an alcohol, and these such lignins can also be isolated. So this is kind of in an overview of what we can do to interfere with such condensation pathways and give us essentially an overview of key stabilization strategies. These are all lignin first key stabilization strategies, and I listed 3 of them here. One is, as I mentioned before, the use of hydrogen and reductive catalytic fractionation setting as means of stabilization of reactive intermediates. This will result in a situation as such that we will get lignin-derived monophenolics, propyl ethyl or propanol phenolics out in a very high yield. And there will be some reduced sugars as well and cellulose-rich polysaccharide pulp, basically. This would be now the Lutebacher chemistry, where you have lignocellulosic biomass and treat it during fractionation with the appropriate concentration of a carbonyl compound, which will then result in this acetal stabilized lignin, which can be isolated or subjected to directly to the next step, which would be a reductive, for example, a reductive treatment, again resulting in, as you see, similar or the same building blocks here in a high yield. The key is here really that these monomers are in high yield. This is the diol chemistry I would like to talk to you about in the second part of my talk. First, I would like to focus on mentioning that when we first, about 2008-9, also PNNL report has presented the top validated platform chemical reports. Everybody knows this, and phenol and BTX were identified as lignin-derived platform chemicals. That was of course very interesting, but these approaches are quite eye-opening, because what it actually shows is that we have some high yielding approach, but it does not result in this case in the formation of phenol or BTX. It does result in the formation of more functionalized molecules, and I think it's fair to say now that these are lignin-derived platform chemicals. Similarly, I would say to, for example, HMF chemistry, where we have to understand how we can take these compounds and channel these into some needed products, essentially, and these are quite functionalized and quite versatile. So we can invoke defunctionalization and functionalization strategies, and this is what I would like to talk to you about first. So obviously, benzene, toluene, and xylene are important, and some other bulk chemicals are very important for the chemical industry. So here is a summary of strategies which we have also mentioned in the ChemSusChem mini review, how to actually get to such very important bulk chemicals or needed BTX and phenol and ethylbenzone in relatively good yield. And what we have to mention is that after lignin first fractionation, there will be the lignin oil, that normally we don't get one compound, although there are some methods that do deliver selectively one compound, but usually this is a mixture of syringil and guaiacyl units. And also on the propyl chain, it can be a propanol, it can be a propyl, it can be an ethyl. So if we consider the formation of bulk chemicals, we have to many groups use the so-called catalytic funneling strategy, where we essentially use the mixtures, or they use the mixtures, and then try to channel the composition into something more uniform. In this case, ethylbenzene can be obtained at about 60% yield on birchwood, which is really amazing. Group of Lee and co-workers have done that. And very important is the formation of phenol. Many groups have investigated this. Bert Hels and Emil Hansen's group, for example. There is a demethoxylation step, usually a dealkylation step, which results in the formation of phenol. I have to mention that, and of course, the recent science paper of the Liao and Sells group, which actually have demonstrated that they can make an integrated lignin-first biorefinery. This is a reductive catalytic fractionation biorefinery, where about almost 80% of the birch wood could be converted to chemicals. So you have the carbohydrate pulp, which is going to bioethanol, for example. The phenolic monomers will be catalytically funneled into 28% of phenol, 98% of propylene, and the phenolic oligomers are also treated and taken care of. They are basically used as printing ink replacement for another compound that was not that green and not that nice. They also provided techno-economic analysis and life cycle analysis and feasibility of such a refinery. So this points out that yes, a strategy can be, for example, made around phenol, but it's not only phenol, but it's a range of other compounds, and this is very important to think in terms of integrated biorefinery schemes. What is very nice is that they show feasibility of such approach, and that it makes really a difference to take lignin out first and valorize lignin in a very efficient way. Similarly, a refinery approach was taken by Rinaldi, for example, as you see here. He has used lignin oils, but it's also an integrated strategy where the carbohydrates will be hydrogen donors, and then the lignin oil will essentially turn into either aliphatic or aromatic compounds, for example, as fuels. Also, Fang and group has reported very nice values for the conversion of such oils to aromatic compounds. Also, nice work I have to mention is the production of terephthalic acid, for example, from again such mixtures. So this would be a catalytic funneling first to this alkyl phenol, and then a carbonylation step. This is the homogeneous catalysis with palladium catalyst, and then an oxidative cleavage of this propyl or ethyl chain to get to the terephthalic acid, the group of Nin Yang has reported. So there are, I would say, this is a very optimistic scenario. We can actually obtain some of the bulk chemicals that we would like to. And I would like to also show a different approach that we have taken. And this was not going to the bulk chemicals, but actually understanding how we can take these lignin-derived platform chemicals and use almost all of the carbon atoms and all of the oxygen atoms that are in the structure. And as you see here, and obviously, if we want to go to bulk chemicals, then we will have to cut off this chain here, and we will lose on atom economy. Obviously, this depends on whether we actually take care of the lost components, let's say. So this is, of course, desired. But basically, here we have to always involve some quite energy-intensive carbon-oxygen cleavage reactions. So we wanted to have something very simple, but clearly this kind of chain is not that useful. And we thought, okay, maybe if we can involve this propyl chain in the formation of an heterocycle, for example, that we put it in a very good use, essentially. And if we look at, for example, such a structure here, this would be tetrahydro-2-benzazepines. Now, if we look in classical organic chemistry, and in 70s, 80s, this was very prevalent, and Katalin, for example, and colleagues have done a lot of work here. There are many synthetic strategies that are basically classical organic chemistry, many steps, very low, high in factor, low atom economies. But of course, the goal was to make these benzodiazepines because they have been identified as very useful for medicinal chemistry applications. So here you can see here some of these structures that are actually very well known for such applications. So we thought maybe this is a good way to go, and we just have to understand how we can get there. So the first task was obviously to have an alcohol to amine transformation, essentially to form a secondary amine in the first place. And we have chosen the amination of this aliphatic alcohol moiety by the borrowing hydrogen method, because this is a method that is clearly a quite sustainable method. It only produces water as side product. I want to also point out already the challenges that we face when we have lignin-derived building blocks, because normally such reaction, you can find many catalytic systems that are able to do this reaction in a selective fashion. However, in the presence of phenol, you face additional difficulties due to catalyst deactivation, or many of these systems use base, and that might interfere with the presence of a free phenol moiety. So such subtle structural considerations really change the chemistry that you have to develop, and we have to always take this into account when we design new chemistries for lignin-derived building blocks. We were very lucky because we have previously identified a base-free hydrogen borrowing method that is based on a Shaw catalyst. And when we have checked this, or actually evaluated this, then we found that we can have a perfect selectivity, especially when we use aniline derivatives to the secondary amine here. So this was very nice for us, and we understood that this can be done in a relatively selective manner, especially with aniline derivatives. However, now we have, of course, a bunch of these secondary amines. Some of these examples can find niche applications, so we are looking into that. But clearly, our goal was to first understand whether we can perform the cyclization. And again, since this building block comes from lignin, we understand that this methoxy is not in the really ideal position for the Pictet-Spengler cyclization to proceed. Again, something coming from the lignin perspective, a hurdle that we have to overcome. But nonetheless, we tried many methods, classical organic methods, and usually we couldn't get a good selectivity to the 7-membered heterocycle. We had a formation of this weird larger microcycle, or we had, of course, competing methylation of this nitrogen. We almost gave up when we understood that we could perhaps use not conventional organic solvents, but essentially emerging non-toxic, recyclable, and biodegradable alternative solvents, which would, for example, the combination of choline chloride and oxalic acid, which has not been used yet in the Pictet-Spengler cyclization, but for us, it worked like a charm. So basically, almost all of our secondary amines, be it guaiacyl or based on syringal unit, underwent a very smooth cyclization without side product formation. So here the solvent is not only a solvent, but actually also catalyzes and facilitates the cyclization step. So we were very happy to see this. And because what we have now is essentially a 3-step process that starts from lignocellulose. One step, the first step, is the reductive catalytic fractionation, essentially lignin first, where we have a good selectivity to this propanol guaiacol. But of course, this is a soup here. So we also have the other aromatic monomers, a little bit, dimers and oligomers and sugars. So here we have really actually a crude mixture that is not that simple. In the review also we mentioned some purification approaches. I don't go into detail here, but what I can say is that we can take this crude mixture without any isolation of this alcohol and directly subject it to the amination protocol that we have developed, and we'll get in a very nice selectivity this amine, the secondary amine. In the next step, then this amine will be subjected to the Pictet-Spengler cyclization, and we get our benzodiazepine derivatives. What we definitely wanted to do is to understand how active in a medicinal chemistry application, or how biologically active are these molecules. And we have, in a collaboration with Anna Hirsch's group, we tested these in a variety of applications against as anti-infectives or anti-cancers agents. And the summary of these studies was that actually about 1/4 of our chemicals were immediately quite active. So they showed quite promising activities in these assays. And this was without any pre-optimization of the structure, just going and checking our library. So we think that this has indeed a potential, and the fact that we can have a very modular and very easy way to modify the structure of these moieties also will help essentially to connect to medicinal chemistry applications. Another point that we have explored quite intensively is the addition of ammonia itself into these very simple platform chemicals. And actually this should be, or it looks like, a very easy reaction, but it's actually not so easy. We have managed to insert ammonia in the form of a nitrile, which was then hydrogenated to the primary amine. So we can get the primary amine, but this is almost more difficult to do than the secondary amines with the ruthenium catalyst. And the nitrile turns out to be a very useful building block, because it can result essentially in an array of useful building blocks. For example, here, the cyclic ketone, we like it a lot. We use it for several purposes, but you can see it is also half of the blockbuster drug donepezil, for example, or some of these styrene derivatives or acid can be used, of course, for the formation of bisphenols, and here also, or functionalized polystyrenes, for example. I also want to mention that if we want to just go for the phenol to aniline transformation with ammonia, this is very, very difficult. And I think we have to, as a community, work more also in these approaches. So we did manage to essentially, via the pseudo halide, go or get to some secondary tertiary amines with nickel catalysis. But again, the reactivity of the catalytic system was really hampered by the presence of this methoxy group here. So it's actually not that simple. For some derivatives, this was fine, but this is again something we will want to look into in more detail. Ideally, it would be nice to activate directly methoxy groups, for example, or in some way even the phenol itself, but that is, of course, a difficult transformation. I would like to also point out another strategy by Bert Maas and group, who actually also found a very clever way to insert nitrogen in the structure, and that was via protection of this phenol, essentially with dimethyl carbonate, then oxidizing this propane chain here, and via the oxime going to a Beckmann rearrangement, and quite regioselectively forming this amide here, which can be alcoholized, and then essentially instead of the propyl chain here, you have inserted a primary amine, really beautiful, so you can get to an aniline derivative. Such derivatives, again, are very nice building blocks for pharmaceuticals, and they have demonstrated in a number of cases, for example, one is shown here, that they can make it from, again, propyl guaiacol, which is, again, one of the main components of reductive catalytic fractionation settings. So this was for the products, and I would like to go a little bit to talk about the use of diol-based protection strategies. So this would essentially mean that we have lignocellulose and we want to have a lignin first fractionation and depolymerization to get to these monomers here. And the stabilization method that we use is the addition of the diol. And this, of course, we base on, we work on this quite a long time now. So this would be essentially the scheme I showed you before, is dehydration and the possible condensation pathways here, or if conditions are right for these productive cleavage pathways that go either to Hebert ketones, these are these C3 fragments, or to this C2 aldehyde here, which we have identified is actually quite responsible for, again, condensation, recondensation phenomena. So we have actually identified the C2 aldehyde, if it can be stabilized by many methods, and ethylene glycol is one of them, then we can actually get to a higher aromatic monomer yields. And we can do this from lignin model compounds and organosolved lignins as well, is what I show you here. What is nice about this diol-based approach, when you use an organosolved lignin, so I point out this is not a lignin first strategy, this is actually processing organosolved lignin. So this is looking at the depolymerization of a organosolved lignin. Here, for example, what you see is the crude mixture is actually the three main components of the crude mixture are the desired C2 acetal. So this is what we like about this kind of chemistry. And here, what you see here on these dots are actually several different organosolved lignins that we have isolated. And here are technical organosolved lignins, and here are some others which with a different kind of beta-O4 content. And there is a trend, of course, there is some connection or some correlation between the beta-O4 content and the acetal yield, obviously. And the method of lignin isolation, however, will affect two key parameters. So this would be a scenario where we isolate the lignin first and then depolymerize. The harsher the conditions that we use to isolate the lignin, the better the lignin yield, but the worse the beta-O4 content. So again, the acetal yield will be affected by this. So there is a trade-off. And of course, the better situation would be if instead of these two steps, like getting the organosolved lignin first and then depolymerizing in a second step, if we would do it essentially in this lignin first setting, where we liberate the lignin from the lignocellulose matrix and immediately depolymerize and stabilize and get to these C2 acetals. As easy as it seems, this took us, again, a long time to explore, because here is a large parameter space to explore. There is acid content, ethylene glycol content, the selection of the organic solvent. Most importantly, to understand, as you see, this is very similar to organosolved pulping conditions. So to understand how can we not get organosolved lignin from these conditions, but actually the monomer. So that is the biggest question. And we did see that there is a large effect of the solvent, but also of the acid content as well as the ethylene glycol content. So there seems to be an optimum for the C2 acetal yield in terms of ethylene glycol and acid content. Too much acid actually results in just amplifying the condensation reactions, and too much ethylene glycol actually shuts down the cleavage reaction, so it actually leads to the ethylene glycol incorporated lignin motifs, essentially. So we need to be in somehow in this range, but again, the range is different for an organosolved lignin or lignocellulose. So when we look at lignocellulose, we have come up with now some usable conditions, let's say, and one of the big finding for us was that dimethyl carbonate, relatively green solvent, was actually very good for this kind of process. And this was one thing. The second thing to realize is that if we are in dimethyl carbonate and adding ethylene glycol and looking for this optimum ethylene glycol level, then we understand that there seems to be an optimum that is related to the degree of delignification. Essentially, what we do here is these are the different fractions of ethylene glycol in the dimethyl carbonate solvent. So increasing the ethylene glycol amount, we are essentially in a mixture of ethylene glycol and dimethyl carbonate. So for these solvent mixtures, the Hildebrand solubility parameters can be calculated. And as we approach, let's say, the Hildebrand parameter of lignin, then as we essentially increase the Hildebrand parameter of the solvent mixture, delignification gets more pronounced here. So there seems to be an optimum for delignification. In terms of the aromatic monomer yield, it stays already consistently the same, around 9%. And if more ethylene glycol is added to this range, then actually the cleavage reaction is already shut down. So basically there seems to be an optimum here where delignification is good and acetal yield seems to be good as well. And if we look at now such a situation in a bit more complex manner, then we have our pine wood, we have dimethyl carbonate, ethylene glycol, and acid. Again, it resembles very much an organosol processing condition. And then what we have though here is not an organosol out, but actually monomers out. So what we can do here is isolate the carbohydrate-rich solid, which essentially is celluloses, and basically subject it to enzymatic hydrolysis. We can get very nice glucose yields out of these celluloses. They look very nice, especially under conditions where good delignification has happened. And here the let's say liquid phase can be subjected to aqueous extraction, where the water phase will contain a number of saccharides. So it will be also ethylene glycol and methanol modified glucoses, as well as mannose, xylose, so basically hemicellulose derived compounds, but we can actually see and quantify them quite well. And then this fraction 1, the DMC phase, can actually also be extracted with toluene, and then basically we can nicely separate the monomers and dimers from some oligomers that are actually ethylene glycol modified lignin oligomers. Actually quite a good fraction, but we can see them, and perhaps in the future we can also try to use them. So it looks like this for now. So we have a lignin first attempt, let's say a diol assisted fractionation, in which lignocellulose is used. A solvent, in this case a dimethyl carbonate, is used, ethylene glycol is added, and I have to mention this is not anymore triphilic acid, but actually we understood that sulfuric acid can be used when lignocellulose is used. So this is very nice. And we can get to a situation where we have about 98% aromatic C2 acetal, and these are from pine wood. So this is actually one main component. And I'm sorry, I don't have the GC traces here, but it's very nice. You have essentially one big signal for your aromatic platform chemical, if you wish. And here you have the cellulose that can be turned about 85% to glucose. And so this would be, let's say, a biorefinery setting that we aim for. Also, of course, we are looking for several applications to turn these aromatic monomers to. And I think with this, I would like to already finish my talk and really thank my group, especially after this moving in a time of lockdown. This was really, really difficult for us, but I think really everyone who contributed to this work. And I would like to also spend a little time to advertise actually the Gordon conference in Lignin Valorization. This will be held July 31st to August 5, 2022. Again, this was postponed due to the corona crisis, but we accept now applications. If you have any questions related to this meeting, please drop us a mail to Yuri Roman or me or Vice Chairs Laura Bartley and Jeremy Lutebacher. I thank you very much for your attention, and I will be happy to answer any of your questions.
So thank you a lot, Katalin, Barta, for an amazing talk and giving a very, very broad perspective of the lignin first and also the details of your recent progresses. We have received a couple of questions, and they are a little bit related, I think. One is from Ali Abdul Kami from Tehran, and the other one is from Rehan Mustafa in Morocco, and they both ask about technical lignins. So have you worked anything with technical lignins? I guess they are alluding to Kraft lignin, for example. How do you separate these, and have you done any of your chemistry on these?
Joseph, I'm not sure my connection is still good. It shows.
Yeah, it's perfect.
Okay, fine. So I can show. Now I have stopped sharing, but I can put back the screen. I can show one of the slides that also involved the depolymerization of technical lignins. Just a second. I will try to do it in this way, and maybe you can already, wait a second, see this. So it in terms of the acidolysis and stabilization method, can you see this screen somehow? Yeah. So you see these green dots here. These are technical lignins. These are relatively low beta of 4 technical lignins, and what you see here is that the actual yield for the C2 acetal is indeed low. So this method is not highly suitable for technical lignins. My view is that technical lignins, they have to be treated in a different way. We have to find a different strategy it should be a markedly different strategy to deal with the technical lignins compared to a lignin first scenario where the idea would be that you don't go towards the route to produce a technical lignin, but actually utilize the native lignin structure. So yeah, this would be my answer.
Yeah, it makes sense, and I think also the lignin first approach is that, as you said in the beginning, it is to prevent lignin from becoming a technical lignin. So
yeah. So our approach with the lignin first is to actually prevent technical lignin formation, and if you do have already massive amounts of technical lignin, I believe you are looking for a different type of catalysis then.
Yeah. We have also another question that is related to lignin, and it is from Kagri Olgun in Stockholm University. And first of all, you're thanked for your lovely presentation. And then the question is, have you worked anything with agricultural lignins? So straw,
yeah, we have some, and we worked quite a bit with walnut shells, for example.
Yeah, I know.
And the straw we also work some, but not that much. So we focus so far more on either pine or some wood lignins, where we can actually identify the source.
Yeah.
But the walnut lignin, for example, that we have, walnut shells that we have explored, these were quite interesting lignins, nutshell lignins. They are very hard, and what we found in our nutshell lignin, that actually it was quite high in the H content, surprisingly.
Yeah.
So I think there are some also opportunities to look there.
Yeah. We have a specific question on slide 10 from Joby Sebastian, and he asks, what is the stoichiometry between the amine and the aryl propanol in the reductive amination?
Yes. So if it's a clean compound, if it's let's say if the alcohol is isolated, then it's actually essentially 1-to-1. So you almost don't have. So it works really nicely.
Yeah.
If we have to fish out the amine from the mixture, then we have to add a little bit more of the amine. And we don't know exactly the reason for this, but we think that is because other type of molecules in the mixture also are involved in the amination reaction that use up the amine. But if it's from the alcohol, it's really 1-to-1 or 1.1. So it's really a very good situation.
Okay, nice. I have one last question. There's several questions, and I had some by myself too. But I think we have to unfortunately finish this seminar with one last question, and that is from Monique Figueredo from EPFL. Is the lignin-derived acetal isolated in high purity from the product mixtures?
Yes. I mean, of course, what I can say is that when we use column chromatography, of course, we aim for a highest purity isolation. So we have a wonderful compound, but column is not our goal here. So we would like to use something else, such as distillation or something similar, extraction. So purification seems to be, of course, a crucial point, and we have to really invest more time, I think everyone really in the field, to understand how we can efficiently purify our products. But the acetal is pure. It's just that, we don't like to use the column.
No. Okay, thank you a lot, Katalin, for this amazing talk, and also for the nice seminar afterwards. And I can recommend you to go into the chat, and then you can maybe have some contact with the audience and answer their question one-to-one. Okay.
Thank you very much.
Thank you. Okay, and then we continue our nice symposium here, and it's a pleasure to introduce the next speaker. So Eric Hegg is a professor at the Department of Biochemistry and Molecular Biology at the Michigan State University in the US. And he's also a faculty member at the Great Lakes Bioenergy Research Center. So the Hegg lab are focused on understanding how microbes catalyze challenging transformation and trying to apply this knowledge to environmentally friendly reactions. And this includes both how enzymes are involved in the global nitrogen cycle, as well as how biomass, for example, lignin and carbohydrates, are depolymerized. And especially relevant to this symposium, Professor Hegg will talk about how enzymes and mimics of how enzymes cleave the beta-O4 bond in lignin. So with this, Professor Eric Hegg will give the talk entitled Biomimetic Lignin Depolymerization Using Small Molecule Thiols, Mimicking the ß-aryl ether Cleavage Pathway. So the screen is all yours.
Okay, thank you very much, Joseph. Let's see if I can do this properly. Okay, are you seeing the right one or the wrong one?
The right one.
Okay, and so so it's a pleasure for me to be here today. I appreciate the opportunity to tell you about some of the work going on in our lab looking at lignin valorization. Before I get started, I want to make sure I thank a couple of people because I always sort of seem to run out of time at the end. And so I want to make sure I acknowledge two really very important people. The first of these on the left here is Gracie Klinger. She was just a fantastic graduate student who just recently graduated and is now working at Janssen Pharmaceuticals. And she performed about 95% of the work that I'll be telling you about today. And the second person I need to acknowledge here is Ned Jackson. Shown on the right, he is my collaborator in the chemistry department at Michigan State University, and together we were the co-advisors of Gracie. So she got a dual PhD in chemistry and in biochemistry. And this work has been funded through the Department of Energy, through the Great Lakes Bioenergy Research Center, and I'm, of course, indebted to them as well. Now, the goal of the Great Lakes Bioenergy Research Center is to convert biomass to biofuels and bioproducts. And just like if you think about a barrel of oil, it is used for many things, and you want to use the entire barrel of oil to make not just fuels but other chemicals. You can think about the plant in really the same sort of sense, right? We want to use the entire plant and to convert it into biofuels and biochemicals. And so while the sugars might be most easily converted into the biofuels, we don't want to forget about the lignin, which can be used in other products as well. And so our goal is to use every sort of piece of the plant to make this an economically as well as an environmentally sustainable process. And so for the purpose of this talk, I'll be focusing, of course, today on the lignin. And what I show you up on top is sort of a generic lignin strand that shows many of the bonds you would find in lignin. And I don't need to tell this audience why it's so important to think about the lignin and why we're interested in it. Suffice it to say that we all know it's very challenging to depolymerize this polymer. And so the goal of this project is really to identify how we can fragment this whole polymer into smaller pieces that can be more easily valorized. We decided to focus on reductive cleavage, in part to maintain the energy content of the lignin, but also to avoid some of the known side reactions that can occur with oxidative methods. And then finally, both because of their prevalence, as well as the ease with which they can be broken down, we were focusing on the beta O4 bonds, like, of course, many other people do as well. Now, this project really started, the genesis of it really started over 5 years ago, I guess now, when Gracie, Lou, Ned, and myself were traveling to a conference. And as we were in the car driving together to this conference, we were talking about a really interesting a family of enzymes, and these are the Lig family of enzymes, which we found very, very intriguing. And what the Lig family of enzymes do is they cleave beta O4 bonds, and the way they do this is via you could say a three-step process. Now, in the first step, what they do is they oxidize the hydroxyl group on the alpha carbon to a ketone. So that's step number one. In step number two, they bring in glutathione, the structure of which is shown up here. It's a tripeptide, but for the interest of this talk, what's really important is this reactive group right here. Okay, so it's a thiol. And so this glutathione then attacks the beta carbon, releasing one of the products, in this case the phenol, and then resulting in this thioether intermediate. And then the third step is another enzyme which brings in another glutathione and reductively eliminates this sulfur from the thioether, resulting in a glutathione disulfide and releasing the final product. Now, in nature, of course, this glutathione, this disulfide, would then be reduced so that you can begin the process again. And so we were talking about that. We were really, really amazed at the chemistry that this family of enzymes did, and we just asked the very simple question: would it be possible for us to mimic this chemistry using small organic thiols? Could we, for instance, develop some sort of oxidative pretreatment that selectively oxidizes this alpha hydroxy group into a ketone, followed by some sort of small organic thiol, which can perform the chemistry we saw up here being used by glutathione in the context of the entire enzyme. And so the very first thing we did was try a very simple reaction. So what Gracie did was she took some sort of model dimer and reacted it with glutathione in the absence of an enzyme. Okay, we just put the two in together and asked the question, what would happen? And so the model that we used was really a very simple model, 2-phenoxyacetophenone. And so we reacted with glutathione in refluxing acetonitrile with a base to a simple base to deprotonate the thiol to the thiolate. And what we saw was that, in fact, we did get a little bit of reaction slowly. And what do I mean by that? Well, first of all, of course, you can see the time. This is an hour. So you're looking at the order of 2 days. And over the course of 2 days, maybe about 25% of the starting material is lost, and a corresponding amount of the phenol is formed. But what we didn't see was any of the acetophenone. And the reason for that, we believe, is that this is pretty bulky. And what happened is we got, again, very slowly, attack on the substrate to generate the thioether intermediate, but that the reaction was sort of dead at that point. So we had two sort of problems. One is that the reaction was incredibly slow, and the second was that it sort of got stuck at this thioether and didn't go any farther. And so what we did was we went back, or what Gracie did was she went back and she screened a number of different reaction conditions, looking at a variety of solvents and temperatures and thiols to try to optimize this reaction. And so what I'm showing you here is, on a single slide, is an enormous amount of work that just included a lot of screening. And so suffice it to say that that if we use small soluble thiols, we can in fact get a reasonable reaction. In fact, if we use the simplest thiol we can think of, sort of beta-mercaptoethanol, what you can see is in the course of about a day, we're able to completely cleave the model dimer, producing basically quantitative amounts of the two products, acetophenone and the phenol. Polar aprotic solvents work the best at moderately elevated temperature, and in fact, the base is required. If you do not deprotonate this thiol to the thiolate, essentially you get no reaction. And so here you can see is just just a few of the various thiols that we tried, again with beta-mercaptoethanol perhaps being the best, which is nice because it's also the simplest and probably the cheapest. And so the next thing we wanted to ask ourselves was whether or not the reaction was occurring in the same manner as the enzyme, because what we know from the literature is that the enzyme works sort of in a two-step process after you get to the ketone, right? Where the first step is the attack of the thiolate to generate this thioether intermediate. But of course, we were not seeing any indication of this thioether intermediate. So what we did was we chemically synthesized the putative intermediate, and in fact you can see how rapidly this decays under the reaction conditions. In just a couple of hours it is completely decayed, and you quantitatively form the corresponding acetophenone, just as you would expect. And so this explains why we never saw the thioether intermediate being formed, was because under our reaction conditions, the first step is the slow step, and the second step is much more rapid. And so then that led us to think about the possibility of improving the rate of the first step to try and trap this putative thioether intermediate. And in fact, if you put on electron withdrawing groups onto the leaving group, you can, in fact, not surprisingly, speed up the rate of the reaction. And now we can identify, shown in red, the thiointermediate, which builds up to a small extent before it continues to decay, and you see only the products at the end. So this is all consistent with an SN2 reaction mechanism, consistent with what is seen in the enzyme, whereby the first step is the nucleophilic attack of the thiolate onto the beta carbon, followed by reductive elimination of the thioether to generate the disulfide and then the corresponding products. And in addition to put on these electron withdrawing groups, we can imagine changing the substituents on both of the rings, both electron withdrawing groups as well as electron donating groups, and generating a Hammett plot. And what you can see is that both regardless of which ring you are modifying, we see a positive slope on the Hammett plot, again consistent with the SN2 reaction mechanism. So then that led us to ask what sorts of other chemistries could go on. What was the scope of the reaction? And one of the things we found out very quickly was, in fact, that if we take this ketone and we reduce it to the alcohol, so in other words, this is the non-oxidized form of the lignin, if you will, you see essentially no reaction, indicating that the oxidation of the alpha hydroxy group to the ketone is absolutely required. And this is exactly what is seen in the enzyme as well. If you don't form that first reaction to take the alcohol to the ketone, you get essentially no reaction. And this is consistent with what exactly you would expect with the oxidation of this carbon to the ketone, activating this beta position and stabilizing the transition state. Now, the other thing we asked ourselves was what sort of substituents could we tolerate on the beta position? Because this is the model that we had been using up to this point. But of course, real lignin doesn't have just the CH2 group here. It actually has a substituent on the beta position. And so first we tried the most simple, where we just put on a methyl group, or we put on two methyl groups, and you can see the rate of the reaction was significantly decreased. We saw, relatively little reaction if we just have one methyl group, and if we have two methyl groups, we essentially completely killed the reaction. So this really worried us about whether this would actually work on real lignin. But then when we made sort of a more realistic lignin model, where we put on a hydroxymethyl group on the beta position, as what you would see in the reaction of real lignin, what we saw actually is very good yield again. And so we were both relieved and pleased with this result, but we're also a little bit surprised, trying to figure out, well, what the heck is going on here? And then we began to look at the products that were being formed a little bit more carefully, and what we realized was, in fact, that this species here was undergoing a retroaldol reaction to regenerate the original 2-phenoxycetophenone starting material, and you can see it building up here, sort of in this orange color, and then this is what's decaying to give rise to the products. Okay, so the reaction does occur as we had hoped, although not exactly the same way we would have necessarily predicted. But nevertheless, we are able to get the desired products in the end, even using a sort of a model that has this hydroxymethyl group on it. Now, this is all well and good, but of course, these are still model complexes. It's not real lignin, and real lignin, of course, has methoxy groups on it. And so we also screened a variety of what I will call more realistic lignin dimers that have, for instance, these methoxy groups. And what you can see is that while this lignin-like functionalization does slow the attack, it does not block the attack. In fact, we still see cleavage of the model dimer. Now, one of the reactions we were a little bit concerned about, or the potential reactions we were concerned about, was this this demethylation reaction. So it is known in the literature that under certain conditions, thiolates can undergo this reaction I'm showing here to demethylate this this methoxyl group. And the problem with that is if you take your thiolate and you create this thioether shown right here, of course the reaction's dead. Right? It can't do anything, and this is sort of a dead end. And so we wanted to make sure that this actually was not happening. And we were very relieved to, in fact, realize that we saw no evidence of this demethylation reaction on the ring, which meant that, in theory, we could be using it on real lignin, just like we had initially proposed. So the next step was to move away from these model dimers and go to some model polymers. And so, what I'm showing you here are 3 polymers that we tested. The first is simply a polymer of the original model dimer that we started with. So this is just a polymer of 2-phenoxyacetophenone, and that's what we sort of term polymer A. Polymer B is very similar, only now we make it slightly more lignin-like by putting on this hydroxymethyl group on it. And then polymer C is the same as polymer A, only it is a reduced form. So instead of having the ketone on the alpha position, we have an alcohol. And not surprisingly, just as we saw with the model dimers, if you have this alcohol, we don't get any reaction. And again, this is completely consistent with what one sees in the enzyme as well. In the case of the model polymers, however, under these reaction conditions, we were asking the question, do we see product? We do see the expected product. And if we were to quantify it, you can see the quantification right here. And so we looked at 2 different simple thiols. We looked at 1,3-propane dithiol as well as the beta-mercaptoethanol. And shown in sort of purple here is the polymer A, and shown in blue is the reactivity of polymer B. And you can see both react relatively well with both of the thiolates, indicating, in fact, that this the thiolates can penetrate, can work on not just dimers, but can penetrate the complexity of a polymer and actually access the beta O4 bond in question, or I should say the oxidized beta O4 in question. And so, of course, we were very happy about that, and so we thought these were very optimistic results, but the question still remained, can the organic thiols actually cleave real lignin, this heterogeneous polymer that's going to have more, of course, than just pure lignin? We try and purify as much as we can, but everyone knows there'll be other components there as well, and there's not just beta O4 bonds, but all sorts of other bonds present as well. And so the question is, can we do this analogous reaction we showed with both the dimers and the simple polymers and break up lignin into the fragments? And so the key questions, of course, is can the thiolates penetrate this complex matrix? Can it access the polymer backbone and be able to get to the beta O4 bond of interest? And then can it react, as we hope, acting as a redox mediator to cleave the beta O4 bond, or will it do some other sort of side reactions, or will it only do one of the reactions, sort of what we saw with the glutathione, but not then do the second reaction, where then we reductively eliminate the thiolate from the thioether, generating this disulfide. So these were the questions we wanted to address, but of course first we needed a source of the lignin. And thankfully, in our lab, we've been generating lignin for quite some time, and so this goes back to a project that really I've been working on for for nearly 10 years now, of generating a pre-treatment strategy whereby we can fractionate the polymers found in wood. We use hybrid poplar as our sort of a model wood species that we use probably 95% of our reactions on, and I don't have time to go through the details, and we've published a lot on this, but suffice it to say that our pre-treatment, which is a copper catalyzed alkaline hydrogen peroxide pre-treatment, the key aspects are that it's under basic conditions and it's an oxidative pre-treatment. And we get two very clean streams. We get a clean sugar stream, which we've demonstrated can be moved on to generate fermentation products, so various biofuels, as well as a very clean soluble lignin stream, which we can precipitate and generate this very nice sort of slightly off-white, we'll call it beige or tan, a lignin. And so this is very different from the lignin that one often sees, this sort of black tar. It's really sort of what I consider a somewhat pristine lignin. And so this is really what initially got us excited about trying to work with this lignin, was because we had never really seen such what I'll call pristine lignin for most of the other pre-treatment strategies that are out there. And when you analyze this lignin by two-dimensional NMR, what you'll see are some spectra that look something like this. And so what I'm showing you on the left is a portion of the spectra of the untreated hybrid poplar lignin. And the important thing is on the right is shown is the same lignin, only this lignin has been isolated using our copper catalyzed AHP process. And you can see two things, hopefully. The first is that qualitatively, the two NMRs are very, very similar. However, there is a distinct difference, and that is you see a few more peaks present in the copper catalyzed oxidized lignin that we have here. And what you see are these two oxidation products. And so if you look at what they are, in fact, we have slightly oxidized the alpha carbon from the alcohol to the ketone. And so what that means is that this copper AHP lignin is actually uniquely susceptible to the thiol-dependent depolymerization I've been telling you about, because we've already partially oxidized the lignin. And so if we take this material and we subject it to either beta-mercaptoethanol or dithiol-3-etol, what you can, and then you separate the products. Shown here is the GPC of the lignin control, and then shown in blue is the beta-mercaptoethanol treated lignin, and shown in sort of orange is the dithiol-3-etol treated lignin. And what you can see very clearly is that there is a change in the molecular weight. And if you quantify that, what you can see is, in fact, that the molecular weight decreases by about 60% relative to the unreacted lignin. Now, the other thing that is very obvious when one looks at this is, in fact, that the polymer abundance, so in other words, the amount of the lignin that can be reprecipitated, also goes down significantly. And in fact, if we quantify that, what we see is on the order of 50% or more of the lignin can no longer be precipitated. In other words, it is now water soluble. All right. And so what we've done is we've broken up the lignin into fragments that are now water soluble. And so you can see this very, very clearly here in the GPC, and this is simply a quantification. And so this then led to the question, well, if it works this well on regular sort of lignin, if you will, what about if we sort of intentionally oxidize the lignin? So we know that our copper AHP P process partially oxidizes the lignin. What if we more fully oxidize the lignin? So we intentionally oxidize it before performing the reaction. And so so we did that experiment. What I'm showing you on the left here is sort of some copper HP isolated lignin, but it's been isolated under slightly different conditions, and the reaction conditions are somewhat different. So we don't get quite nearly the same sort of oxidation process in the beginning. And then we react it with a thiol, and you in fact can see, looking at the GPC again, that there is a shift in the molecular weight. However, if we intentionally oxidize the lignin first using sort of a Bobbitt salt type oxidation done in collaboration with Professor Shannon Stahl at the University of Wisconsin, what you can see is that the thiol treated oxidized lignin see a much bigger change in the extent of the depolymerization. And of course, we can quantify that. And in the interest of time, I won't go through all of the various bar graphs. But what I do want to do is very quickly address the question of what are we forming. And I'd like to say we've completely figured it out. We haven't. We're still in the process of analyzing all of the products. But what I want you to do for the moment is just focus on the pie chart on your left. And the pie chart on the left shows that we are generating, not surprisingly, a mixture of oligomers, tetramers, trimers, dimers, and monomers in the product following the thiol treatment of this oxidized lignin. And then shown in the numbers below is the change that you see in the amount of this various species, both before and after treatment with the thiolate. So not surprisingly, we see about a 20% decrease in the number of oligomers we see, and then about a corresponding 15% increase in the number of dimers that we see, for instance. And so we can, what this sort of quantitatively shows you is that, in fact, we are breaking down the lignin into smaller fragments, mostly into dimers with some trimers and tetramers as well. And so what are the key take-home messages? The first is that we can mimic this very elegant enzymatic pathway using sort of an oxidative pretreatment followed by some very simple small organic thiols, which can penetrate the complex matrix of the polymer, access the now oxidized beta O4 bonds, resulting in cleavage of the lignin, and it follows a two-step enzymatic, a two-step SN2 type reaction, similar to what is going on in the enzyme. What are some future directions? Well, the first future direction, of course, is figuring out how to recycle this disulfide. And so that's what we're in the process of doing right now, because in the real enzyme system, this would get recycled back to generate another free glutathione, and that's what we are doing. And there is another a student in the lab, a relatively new postdoctoral student, Zhen Fang, working on this project. And what does this look like? Well, what we can envision, of course, is where we have the initial attack, just like we saw with the normal sort of enzymatic reaction, generating this disulfide, which can then be electrochemically reduced to generate the thiolate, which could then continue the reaction again. And so we're a spoiler alert is that it's some very interesting, exciting reaction that's going on. It's more complex than we initially thought. We're putting the final touches on our manuscript right now, so stay tuned, and hopefully this will be out in the literature by Christmas. You'll be able to at least see an online version of it, and so it's very, very promising. And so with that, I will stop and answer any questions that you may have.
So thank you, Eric, for a fantastic talk. I was really amazed by this. And the first question that I had actually along the whole talk was, where are these enzymes naturally occurring? Because I always learned that there's nothing that degrades lignin.
Right. So I'm not a microbiologist, but there are these soil bacteria, among other things, as well as well, I believe I think it's mostly found in soil bacteria, and unfortunately I took out a slide that shows sort of the complex pathway. This is actually just one pathway. There are more out there. The complicating fact of this is that if you think about this soil, the soil bacteria, the reactions that have been most characterized are those working on dimers or maybe trimers, things that get into the cell. Intracellular enzymes, and so clearly there must be some way for the microbes to break down the lignin into smaller fragments that can then get into the cell. Exactly how this occurs, I would say, is still a bit of a black box. Whether some of these enzymes can be secreted, or whether or not there's different enzymes which are secreted, or they're relying on some other microbe that then partially breaks down the lignin and then brings them into the cell, is still, I would say, largely unknown. But again, I'm not a microbiologist, and so there's people out there who know about this a lot more than I do.
Yeah. Okay, thank you. So we have a few questions here, and one is from the coming up speaker, Professor Claudia Crestini. Very interesting work. Did you try to isolate residual dimers and trimers to clarify their structure?
So I presume you're talking on the actual lignin reactions, and the answer is that's exactly what we're in the process of trying to do now. It's, as you can imagine, it's a complex, challenging process. And unfortunately, Grace, or fortunately for her, of course, she graduated and is now working in industry. So we've had to recruit somebody else. But yeah, we were working on it. It's a great question, because lignin, of course, has multiple types of linkages, not just the beta-O4. And we have also begun to ask the question, is it possible they can, under certain conditions, attack some of these other linkages as well? And so we've looked at, for instance, some other ether linkages, and it looks like under certain circumstances you can get a small amount of cleavage at some of these other linkages as well. So that's exactly the type of thing we're trying to do, really understand exactly what are the products we're forming.
Okay, thank you. We have a question from Zhenli Zhang. Hi, Eric. Thanks for a nice presentation. I'm Changzhi from Groningen in the Netherlands. My question is it possible to do the oxidation and the thiol cleavage in one pot? I think that is what you showed in the last slide with the electrochemistry, right?
Right, sure. That's exactly. So the holy grail, of course, would be to do, well, I don't have the slide up here right now, but if you think about it, right, it's a 2-electron oxidation as well as a 2-electron reduction. So what one, to regenerate the thiolate. And so what one could imagine is having sort of an electroneutral process where the electrons that are used to do the oxidation are the exact same electrons which are used subsequently to re-reduce the disulfide. So that's the holy grail, but we really are just beginning to scratch the surface. And as I mentioned sort of at the end of the talk, we have some really exciting results when we're starting to do this reaction in the presence of some sort of electrochemistry. And while it's exciting, I can tell you it's not nearly as straightforward as we thought it was going to be. So again, stay tuned.
Yeah. So you have a lot of questions posted in the chat, Eric, and I think we will not be able to solve all of these during the seminar. So I please ask you to go into the chat and answer these questions. And
right.
I want to thank on behalf of everyone for a very inspiring talk. And yeah, it was really amazing. Thank you.
All right. Well, thank you for your time, and thanks for listening.
Yeah. Okay, then we go to the third speaker, Claudia Crestini, who is since 2018 a professor at the University of Venice, Foscari, in Italy. And before this, she was a professor in Rome at Tor Vergata University. So the research of Crestini's lab focuses on elucidating the structure of a complex lignin. And I think some of the questions that Eric got, maybe Claudia can sort out. And she has also taken very challenging elucidation of softwood croft lignin. And she also has worked on fractionating these different types of lignin and found different structural differences of these. And also, she's working on finding applications for these different fractions. For example, lignin nanoparticles. So I welcome up Professor Claudia Crestini with the title New Perspectives in Lignin Valorization, Nanoparticles and Nanocapsules. The screen is yours.
Thank you, Joseph, for the kind introduction. Good morning and good afternoon, everybody. Yes, I will try today to, let me share the screen. I will try today to show you a possible new approach to lignin valorization, an approach that can be starting from a completely different perspective in the treatment of lignin. As you may know, I've been working on the topic, on the issue of lignin valorization since about 13 years so far. And what is clear, also from the previous presentations that we saw, is that approaching lignin valorization requires a huge effort. And is nowadays focused mainly in the development of new reactions aimed at controlling a number of issues in lignin, at avoiding the formation, for example, of technical lignins because they are very difficult to treat or to depolymerize. Now, so up to now, as all we know, lignin potential is basically not fully exploited, and but all we are aware of the fact that lignin has a number of possible opportunities that we cannot waste. Besides being the most abundant aromatic biopolymer, it has some unique properties that sometimes we tend to forget that we should try to exploit at the maximum. I'm talking about the specific amphiphilic backbone that is given by the phenyl units, by the aliphatic side chains on one side and by the phenolic moieties on the other side, that make lignins species with a unique amphiphilic backbone that have a special tendency to pi staking and to generate complexes. And when we couple this to its high biocompatibility, lignin is edible, and antioxidant activity and its UV screen properties, together with a number of biological activities such as anti-inflammatory, antimicrobial, anti-tumoral activity, well, these are huge opportunities that we should exploit somehow. And to do so, we need to overcome the endless lignin biorefinery challenges, which I like to sum up in three main issues, which are a fundamental poor understanding of structure and chemistry, because lignins are rather complex, the extreme heterogeneity, variability, and diversity. So this is, in my opinion, the highest challenge that we have to face. Lignin are different from the botanical origin, harvesting time, but also on processing methodologies, which end up in a number of different technical lignin that are available on the market that are basically very difficult to upgrade. So we have to overcome this problem. And the different approaches have been tried. Lignin first is one of them. Other approaches are related to lignin fractionation in order to get reliable and consistent samples. And a third problem is due to the low control and tuning of the multifunctionality of the technical lignins. So, looking at the problem from this perspective and looking at the industrial needs that are basically processes with low environmental and energetic impact, we need, in my view, a change in the perspective. So we could, for example, start from here. Do we need to chemically modify lignin? Do we need to upgrade lignin? Or can we just simply exploit the tendency of lignins to undergo supramolecular assembly and to tune not the chemical moieties in lignin, but the chemical physical properties as a whole? So, in other words, can we transform the different technical lignins into nanomaterials and use them? First of all, we should ask ourselves which kind of application we could aim at. And if we look at nanoparticles, nanoparticles have a huge range of possible applications, ranging from antimicrobial, pesticides, pharmaceuticals, and so on and so forth. Now, this list in this slide is trying to tell you how it is possible to use nanomaterials directly in industry. And our aim is to develop this kind of products to answer direct industrial needs. For example, all these nanoparticles applications now are carried out by microplastics, which we need to reduce. We have European laws that are aiming at reducing microplastic pollution. We don't think about that, but most of food, different additives in composites, in flowers, in all kinds of household or person care products are full of microplastics that need to be replaced somehow. So in this perspective, the objective of our work has been to create synergy-enhanced active delivery systems. Delivery systems based on the lignin backbone that could somehow deliver active materials such as drugs or flowers or phytochemicals or whatever in a controlled way, but without the use of cross-linking agents or any kind of chemical functionalization, in a way that we could get the maximum synergistic effect between the matrix of the lignin, which constitutes these particles, and the loaded actives. All of these should be developed through a fast, green, sustainable, and scalable synthetic approach. And the final capsules, the final particles should be stimuli responsive. So we are trying to transform a technical lignin, which is basically a waste, a black, dark, ugly waste, into something that is smart and green. So first approaches two nanomaterials were aimed toward the obtention of lignin nanoparticles. Our original work was carried out by Sonication in 2015, and after that, many other efforts have been carried out in order to obtain lignin nanoparticles. Such colloidal dispersion of lignin can be easily obtained just generating a lignin solution in a suitable solvent and diluting with a non-solvent, for example, water. Those of you who are old enough to remember that at the old times, we used to isolate milkwood lignin by dissolving lignin into dioxane and then diluting that with water to precipitate lignin. And it was a nightmare in the lab because we got always this opalescent system and lignin was never precipitating. Now it was 30 years ago, and now we know that they were lignin colloidal dispersion. They were lignin nanoparticles that, of course, did not tend to precipitate in high yields. But this is to say that these lignin nanoparticles are quite stable, and we can make them in the laboratory and use dialysis bags to get pure lignin nanoparticles with beautiful delivery kinetics, and we can entrap in these lignin nanoparticles a lot of materials. And there are now a number of different systems to generate these nanoparticles, such as, for example, the solvent-solvent system or the hydrotrope system, which consists basically in the generation of a lignin solution into sodium paratoluene sulfonate, which is diluted with water and allows to isolate lignin nanoparticles of a high purity with a solution that is directly recyclable. So the sodium paratoluene sulfonate can be recycled. Now, these particles have a very nice characteristics. They are they have a quite low polydispersity and are about 300 nanometers of dimension, as it can be seen from different analytical techniques. If we analyze them by the zeta sizer, we see their real dimension as if when we analyze them by scanning electron microscopy, while if we use other techniques such as light scattering, we see bigger dimensions. But still, we have nice materials, and so far, many compounds have been entrapped into these vectors. Most of them being insecticides, herbicides, and microbiocides. Now, I was mentioning before that first we have been isolating lignin nanoparticles by ultrasound treatments. We think that this treatment is especially interesting because it's easy to use, is clean, is sustainable, and it consists in a double process. One is a physical effect due to acoustic cavitation, which generates microbubbles that grow and collapse. In this growth and collapse, we have the generation of locally very high temperatures up to 5,000 degrees and 2,000 atmosphere, very high pressures. So locally we can have significant reaction while we get still a solution which is room temperature. So these strong physical effects end out, according to the power of the ultrasounds, in the creation of reactive radical species and initiation of different reactions in case we need them. So the first time we were using ultrasounds to make lignin particles, actually we got also something different. And to be honest, we got mainly something different. This something different is hollow nanoparticles. We can simply make an oil and water emulsion of a solution of lignin, which is the brown vial that you see on the left, and we can simply sonicate it during 40 seconds. What we get is something that for us was very exciting, because what we get is this off-white foam. This off-white foam is lignin hollow nanoparticles. So, first of all, transforming lignin into hollow nanoparticles has a main huge advantage. We get rid of the color of lignin. Why does this happen? Simply because the dimension of the nanoparticles are such to have a huge light scattering, and therefore we cannot see the color of lignin anymore. These particles are bigger than lignin nanoparticles, are around 1 to 2 microns. This dimension is very interesting because it allows us to use them for drugs delivery, for any kind of human use, which is not easy to be done with nanomaterials as well. Also, we have been, this is a ChemSusChem image of these capsules. As you can see, we have a very thin skin, and the skin is the lignin skin, and inside we have the active, which is entrapped. Now, we have been investigating different lignins, different conditions, and we found that this is a very general procedure, which is suitable for any kind of lignin. We used also lignosulfonates to make capsules, and it's very robust. Of course, we can optimize the size, distribution of the capsules according to sonication. But what is also very interesting is that, the structure of the lignin in the skin of the capsules is different from the starting material. More specifically, if the red line is Kraft lignin, the lignin capsules are the light green, have a higher molecular weight distribution, meaning that this is a way of selecting higher molecular weight fraction of lignin to generate the outside of the capsule. And also the distribution of the phenolic groups, the total phenolic groups in the capsules is lower rather than in the starting lignin. Is this process really general? I would say yes, because what happens, what happens is that we can also take tannins, other kind of natural polyphenols, which can be either condensed or hydrolyzable, or even complex tannins and monomeric tannins to generate capsules. This means that we don't need high molecular weight polymers or oligomers to make a capsule, but that we simply can exploit the tendency to aggregate. Also, changing the condition of sonication, we can, under low power conditions, have a simple pi-staking of the tannins to generate the capsules, while when we sonicate at higher powers, we induce the formation of radical species and we get the capsules with a higher molecular weight than the starting tannin or lignin. So we can conclude that the polyphenol-based capsules are held together by, on one side, oxidative coupling generated by the coupling of the phenoxy radicals that are generating urisonication, and on the other side, on the pi-stacking interactions. And this can be tuned according to the power of sonication. Now, in order to develop a synergy-enhanced active delivery, which can be used for human applications, we need a higher biocompatibility. A number of studies that we have been carried out in collaboration with geneticists and microbiologists, show that these capsules can be efficiently incorporated into mammalian cell cytoplasm, and they are actually stratified upon the nucleus of the cell, but they are neither cytotoxic nor genotoxic. So they are promising vectors for active delivery, especially because they have radical scavenger and UV absorption characteristics, which can help protecting the active inside. Also, they show the very high stability into common cosmetic media, so they are suitable for topic application. Here, I want to show you a case of study of treatments against bees diseases. As you know, there is a problem in bees which are easily attacked by microorganisms and fungi. Well, we encapsulated 4-bromothymol, which is a new antibacterial, antifungal, and antiparasitic drug, into lignin nanoparticles, and we found a significant reduction of these bee pests. Also, lignin and tannin microcapsules can be generated in a hybrid form. We first synthesized iron lignin and iron tannin complexes in order to get an additional network in order to improve the capsule's stability. And then submitted the tannins chelated with iron to and the lignins chelated with iron to sonication to get a material which is definitely more resistant, with much higher loading factors. This kind of hybrid iron particles are very interesting and have been applied in a second case of study, which is the delivery of an anti-tuberculosis active, which is called BM635. This is a new anti-tuberculosis agent. The problem of tuberculosis is that delivery of the active substances in the lungs is very difficult. So our idea was to generate an aerosol formulation in which the anti-tuberculosis active was entrapped into a lignin or a tannin capsule. What happens in this case is that the capsules manage to open in surfactant mediums that mimic the environment in the lungs. What is interesting here is that not only we have a zero-order release kinetic, which means that we have a constant release of the active upon time, but especially the fact that the Mycobacterium of tuberculosis has an iron-dependent metabolism. That means that once the tuberculosis Mycobacterium gets in contact with the capsule, it chooses to eat the iron and cleaves the capsules and basically commits suicide. So this is a sort of smart delivery of our active. But there are also other ways to induce disassembly of these nano capsules, which are a little bit more, I would say, smart. First of all, different buffers that we can use present different salinity content, which depends on the concentration, of course, and different ion distribution. Now, lignin and tannin capsules are completely stable in water. When we change the salinity, we manage to affect the stability and we manage to trigger active release. But we manage to control it in a very fine way. we can divide the different ions into the Hofmeister series, which ranks the influence of the ions on the physical behavior on a wide variety of aqueous processes, ranging from colloidal assembly to protein folding. And this depends upon direct ion macromolecule interactions and also on the interaction with water molecules in the first hydration cell of the macromolecule. Now, these ions can be either cosmotropic or chaotropic. The cosmotropic are strongly hydrated and have a stabilizing and salting out effect on colloidal suspension, while chaotropes have a surface tension decrease effect and the solubilizing effect, and fundamentally cause solubilization. So if we study the stability of our capsules in sodium chloride with different increasing concentration, we can see that the stability index of our capsules goes down. If we change the salt, for example, we go to phosphate, well, with the phosphate, we have the same behavior. Increasing of salinity corresponds to decrease of stability. But if we change the kind of salts that we use, for example, here we have pure water, stability index 1, sodium chloride, at the salinity of 10 ppt, we have a stability of about 65%. If we change the salt to a cosmotropic buffer, we can see that even increasing the salinity, we do not have a significant decrease of the stability. So triggering or changing the nature of the ions of the solution can trigger the release of the active these capsules. Also, pH can trigger the release, and more specifically, we can have that under alkaline conditions, our capsules are stable. In chaotropic ions, they are stable, while, in cosmotropic ions, they are stable, as well as at high temperature and pressures. While when we go to acidic conditions, these capsules can release their actives. So, to conclude, natural polyphenol self-assembly can be used to develop and to generate hollow nanoparticles and nanoparticles for the development of synergy-enhanced stimuli-responsive active release vectors. These materials are very interesting, and now we are able to generate them on a kilogram scale, and are very promising because they have neither site or genotoxic activity, and they are efficiently incorporated. They are super stable in commercial cosmetic media, and they are under study right now in a number of applications in the cosmetic field, agricultural, pharmaceutical, and food field. I would like to state once more that this is a completely alternative approach which allows valorization of lignin without the need, in this case, for a chemical modification. And finally, I would like to thank my research group that recently changed because I moved to Venice, who has been helping me in these days to set up a completely new lab, and all of you for the kind attention.
Thank you so much, Claudia, for an amazing talk. And it's a pity with these Zoom or these virtual talks that you will not hear the applause, but this is something I really miss. But it's a very nice talk, and there's a lot of questions, so I go directly to them. So how how did you study? You showed structures of the. This is by Katalin Barta. You showed structures of the iron complex lignin structures. How did you study the structures of this? Were you able to do that?
Okay, we started from model compounds and from the I'm trying to share again the presentation. Here it is. Okay. We started from the structure of simple monomeric complexes. This is not quite easy because iron complexes are very complicated, have very complicated structures according to the pH and the nature of the ligands. Basically, it depends on the number of catechol that are present in the lignin. Our study was started trying to work in an equimolecular amount of iron ions and catecholic moieties in such a way we couldn't have an excess of iron. So we were also going through different amounts of iron in order to see how it could assemble. Of course, these are the basis for iron ink preparation. So once you get the complex, it's very difficult to analyze it directly. But we have been working with the Raman characterization of this material.
Okay, thank you. And the oxidation state of the iron, you have showed that it's iron 3, so it's not reduced. Yeah.
Yeah, iron 3.
Okay. Then you have a question here by an old friend of yours, Mika Siponen. Hi, Claudia. Thank you for a very inspiring talk. My question is, 1, what is the most promising route to improve targeting of LMPs to specific sites? And then the second question is, how biodegradable are the LMPs in the environment and physical media?
Hi, Mika. How are you doing? Thank you for this question. Good to hear from you. Okay. The most promising route to improve targeting in a special site, it depends on the kind of application that you are looking for. I'm trying to be more specific. What I mean here is that if we are aiming at a drug delivery, then what we can do is directly functionalizing the lignin with the specific antenna, specific receptors. And we have done it for drug delivery for tumor, ovary tumor treatments. Or we can try to tune the dimensions of the capsule for passive delivery. This is another possible targeting. About biodegradation, I could say that lignin is fully biodegradable. So lignin particles are basically the same, since they can simply open up by triggering the pH or the salinity. And I showed you that there are different powers you can treat the capsules, and we usually work at low power sonication powers in such a way that we do not have a cross-linking of the lignin. So it basically doesn't change from the structural point of view.
Okay, thank you a lot again, Claudia. And you also have several more questions in the chat. And unfortunately, we'll have to close the seminar with you, the oral seminar, but you can continue chatting and answer these questions maybe. And then I have to,
thank you.
Yeah. And then I have to go to the last but not the least talk today. And it's a great pleasure to welcome Changzhi Li, who's a professor at Dalian Institute of Chemical Physics, where he also received his PhD degree in 2009 under the supervision of Professor Zhongbao Zhao. He has then worked also for Tao Zhang's group, who's very famous on the lignin depolymerization, and he became a full professor only last year. He has a broad research portfolio, and he's pioneered in the ionic liquid mediated cellulose hydrolysis technology. He has also worked a lot on lignin depolymerization and also on the strategies for production of aromatic compounds from the available bio-based platform compounds. And he also uses green and sustainable chemistry routes. So with this, I welcome up Professor Changzhi Li with the talk, Catalytic Valorization of Lignin Towards Selective Strategies. So the screen is yours, Changzhi.
Thank you, Joseph, so much for your kind introduction. And now I will share my screen. Can you see my screen? Yes.
Yes. Yes.
Okay. So let me. Okay.
Perfect.
Thank you, Joseph. And I also would like to thank ChemSusChem giving me this opportunity to share our work. Today, I will talk about our recent progress on the selectively conversion of lignin. About 70 million tons of lignin is being produced annually. However, only 5% is used in commercial application. Therefore, efficient valorization of lignin into value-added products would play a key role in improving the economics of the overall biorefinery process. Our recent published paper gives a summary of the advances in the production of chemicals and fuels from lignin. More recently, several elegant technologies such as further catalysis, two-step strategies, and the lignin-first concept are also developed. To realize the depolymerization of lignin in a selective way, generally, the key points show the focus on a robust multifunctional catalyst and innovative routes so as to selectively activate the CO and CC bonds. According to the above background, our group focuses on these 5 methods. We wish to realize high selective activation of lignin CO bonds, replace noble metal catalyst, avoiding consumption of reducing agents or oxidants, so as to meet the green chemistry concept and obtain useful chemicals and fuels. So today, I will introduce our progress on selectively convert lignin into monophenyls, aromatic ketones, and arenes and lectins. And this picture shows the representative lignin structure model with typical linkages and the common aromatic units. If the linkages can be selectively cleaved, then monophenyls can be produced. Our group ever studied the tungsten carbide catalyst for hydrogen decomposition and observed the palladium-like catalytic performance. In addition, tungsten carbide has acidic sites on the surface due to the superficial oxide. Based on these properties, our group recently opened a new route for the catalytic conversion of cellulose to ethylene glycol using tungsten carbide catalyst. The critical step of this process is cellulose hydrolysis, super-Richter-Adler reaction, and hydrogenation reaction. The successful cellulose conversion and the platinum-like behavior of tungsten carbide provoke us to consider, is it possible for the conversion of lignin feedstocks, a highly recalcitrant material with different structure? With this motivation, we tried the conversion of lignin using tungsten carbide supported on carbon. Fortunately, such catalyst showed excellent performance. It showed a comparative activity with noble metal catalyst while the benzyl selectivity is significantly higher than noble metal catalyst. And with this reaction pathway study indicates this is a three-step process initiated by acetic catalyzed dehydration reaction. And the surface species of tungsten carbide were very complex, particularly in aqueous solution. And to figure out the active species, the catalyst with designed tungsten species were synthesized by controlling heating treatment temperature. The correlations between the surface tungsten species and the conversion results are detailed studied. It was found that with the increasing of treatment temperature, there was a clear evolution of the tungsten species from tungsten oxide to tungsten and then to tungsten carbide, along with the decrease of acid sites and the increase of the metallic sites. In the conversion of beta-O4 motor compound, a clear synergistic effect was disclosed. And that is surface tungsten oxide acting as the acetate sites and in charge of initial dehydration, while the metallic tungsten carbide sites promoted the hydrogenolysis reaction. The catalyst with balanced tungsten trioxide and tungsten carbide species provide a much higher yield of beta-O4 cleavage products. We further studied the correlation between the lignin structure and the activity of the tungsten carbide. We found that the linkages basically determined the reactivity of lignin, as beta-O4 is the most frequency linkages in all lignin. Its chemical reactivity dictates considerably the resistance of lignin to chemical digestion, while the product's distribution is mainly determined by aromatic types and the functional group. Thus, G-type lignin is preferable for selectively valorization. While tungsten carbide shows potential in lignin depolymerization, we showed ecology that it does not work for all the CO bonds. For instance, birchwood lignin oil have large amount of oligomers after reaction. So how to improve the conversion efficiency? Bimetallic catalysis offers the opportunity to modify the catalyst property and tailor the selected to a particular product. Noting that noble metal catalysts possess high activity in hydrogenation reaction, we then tried adding noble metal to improve the performance. As expected, in lignin hydrogenolysis reaction, tungsten-based bimetallic catalysts not only modulate the hydrogenolysis reaction, but also suppress the over-hydrogenation of the benzyl ring that avoid the formation of cycloalkane. Moreover, such bimetallic catalyst shows better stability than tungsten carbide alone. Another example for the activation of stubborn linkage is the cleavage of 405, the most inactive ether linkages in lignin. Previous published method use strong reductant on the harsh conditions or need strong bases. In this work, we developed an efficient method for the transfer cleavage of the 405 motor compounds using isopropanol as the hydrogen donor of a nickel aluminum oxide catalyst. The high activity is attributed to its high dispersion and the proper nanoparticle size and a relatively high ratio of metal nickel. The reaction avoids the use of hydrogen gas, reveal an environmentally friendly approach to depolymerize lignin. Another good example avoid the use of hydrogen gas is the rhenium catalysis. As Professor Crestini and Professor Kuhn have done lots of excellent work using rhenium catalyst for lignin conversion. It is interesting that several groups, including Toast, Aboma, Tomishk, disclosed that MTU catalyzed the DO-DH reaction of polyols into olefin, noting that lignin has certain amount of side chain hydroxy group. We developed a fast DO-DH induced lignin depolymerization of MTU in our liquid. A series of lignin model compounds, including organoso lignin, were converted to monomer in 2 minutes. The combination of lignin and microwave irradiation ensures this fast conversion. First, the dissolved lignin in our liquid overcomes the heterogeneous nature of lignin and making the catalyst more accessible to the substrates. And more importantly, lignin has excellent properties for transformation of microwave into heating. But homogeneous catalyst in our liquid suffers separation problems. So a heterogeneous rhenium oxide catalyst was prepared by impregnating carbon with an aqueous solution of rhenium precursor. Such a catalyst exhibited good activity for the cleavage of different Cu bonds in isopropanol. Most of alpha O4 and beta O4 model compounds can be cleaved to corresponding monomers in moderate to good yields. Then we explored the reaction route using typical beta O4 model compounds by monitoring the time course, control experiments, and isotopically labeling experiments. We finally determined 3 pathways from the transformation of beta O4 linkage, among which the reaction started from dehydration is preferred. Hence, the heterogeneous rhenium catalysis also initiated by the DO-DH reaction, and isopropanol played a key hydrogen donor in this hydrogen transfer pathway. Characterization of the catalyst indicates that rhenium with 4 to 6 valence is the active species for Cu bond activation. From the atom economic and green chemistry viewpoints, the reaction without adding oxidants or reductants would be more ideal. Several researchers, such as Bergman and Hutchins and Hardwig, have shown the potential for the redox neutral cleavage of different linkage in lignin model compound. But structurally well-defined homogeneous catalysts have rarely been reported for the conversion of real lignin, although they might be superior in terms of mass transfer and may offer milder conditions. In this work, we developed a mild redox neutral lignin depolymerization system featuring a water-soluble binuclear rhodium complex. This catalytic system could be successfully applied to the depolymerization of a lignin-like polymer, and alkyl-lignin, and even raw lignocellulose samples to produce aromatic ketones, providing a homogeneous catalytic system for lignin first biorefinery in water. Mechanism study by deuterium labeling shows that the hydrogen used for cleave of the Cu bonds originated from the alcohol moiety in a substrate, suggesting that reaction proceeded via a metal catalyzed dehydration step to afford a carbon intermediate, followed by Cu bond cleavage to afford ketone and phenol products. One major challenge for the homogeneous catalyst is the recyclability. The binuclear rhodium catalyst is water soluble, while the products are not soluble in water. So they are easily extracted with organic solvent, and the solvent containing the catalyst could be reused at least 18 times. In our latest progress, a more simple rhodium catalyst showed competitive activity, while only half loading amount was needed, comparing with binuclear rhodium complex. The above cases all focused on depolymerization of lignin to phenol. The second case I want to talk is the conversion of lignin to aromatic ketones. This work is finished in collaboration with Professor Westenwood. Oxidation cracking of lignin would generate aromatic ketones product. However, it is really challenging to control the selectivity. Generally, the product is a mixture of aromatic aldehyde, ketones, acids, and different excessively oxidation products due to the complex structure of lignin. Recent work by Starr and other researchers proposed an interesting approach involving an initial oxidation of the beta-O4 linkage followed by cleavage of the ß-aryl bonds. The first oxidation step is expected to lower the bond energy of the aryl ether and thus benefit for improving the degradation efficiency. Such a two-step strategy has been confirmed by the conversion of different beta-O4 model compounds. Though several groups have achieved oxidative modification of lignin using a variety of oxidants, precisely control the oxidation extent has not yet been studied. Particularly, the oxidation of linkages beyond the beta-O4 is not concerned. Here, we extended the current level to understand of the material lignin ox, generating it by reacting with DDQ as an oxidant under different conditions. Our study initiated with typical model compound like beta-O4. By optimizing the oxidation condition and control the DDQ amount, the oxidation step can be rationally controlled. Then we further showed that it is possible to form different types of lignin ox, depending on the oxidation condition that are used. With this protocol, we can form a well-defined lignin ox from 6 different hardwood lignins. Lignin ox can modify considerably in structure depending on the details of the oxidation protocol. And in turn, the solubility and some other property can then be tuned for different use. With this special lignin ox in hand, our subsequent work tested the reductive depolymerization using tungsten carbide and other typical noble metal catalysts. It was found that the selectivity for aromatic products was shifted from alkyphenols to aromatic ketones when lignin was replaced by lignin ox as the substrate. On the other hand, a negative influence on lignin depolymerization was observed. That is, lower monomer yield from lignin ox were observed than from lignin itself. This result was unexpected, as it is contrasted with the model compound study. This picture shows the model compound beta-O4 conversion results. Oxidative pretreatment indeed improved the monomer yields. So the reason behind the conflicting results were explored. Our results showed that the degradation of weak linkages occurred during the oxidation treatment. And the second reason is by HSQC, we can analysis indicate that the repolymerization of the active species may take place. These two reasons made the lignin ox is indeed more recalcitrant for degradation. Nevertheless, our work demonstrated that such an integrated process offers a highly selective strategy for aromatic ketone production from lignin. Lignin seems to be an ideal resource for iron if all the oxygen can be removed without destroying the benzene. Indeed, it is not a big task for the deoxygenation of most oxygen-containing group in lignin, except that the iron CO bond in phenols due to its high bond dissociation energy. Despite some good catalytic systems have been reported, however, concurrent hydrogenation of benzorin is hard to avoid. In this work, we show our progress on the deoxygenation of lignin for the production of aryls. First, a two-step strategy for the mild preparation of cobalt and mobalium sulfide catalyst was developed. This process utilizes the reducibility of mobalium sulfide and avoid the high temperature for the reduction of cobalt precursor, which ensures the good disposition and of metallic cobalt on mobalium sulfide and facilitate the formation of metal vacancy interface. In the HDU of various lignin-derived thinners and real bio-oils, such a catalyst exhibited an excellent activity and high deoxygenation selectivity, even at extremely low temperature of 120 degrees C, which is far below the lowest reported reaction temperature so far. For without destroying the benzorin, our characterization indicating that metal vacancy interface and electric transfer between cobalt and mobalium sulfide induce the catalyst and unprecedented HDU activity for the upgrading of lignin oil to aryans. Our newest progress recently scanned different support using mobalium sulfide as the active species for the selectively methoxy removal. For mobalium sulfide acid supporting active carbon, it features with plenty of acid sites, high surface area, and more exposed metallic sites than other supported catalysts. Therefore, it earned a good methoxy removal ability. The last work I want to share is the one-port complete hydrogenation of lignin into lefsens. Our previous work has shown the ability of rhenium for lignin depolymerization. In this work, the deoxygenation and the hydrogenation ability were greatly improved by adding iridium species. It offers us a direct one-port route from lignin to lefsen fuels. Then our work studied with screen different metal species and supports. Iridium modified rhenium oxide supported silicon oxide exhibited the best performance in beta-O4 mold compound conversion. Then the conversion of various lignin model compounds was conducted, and to assess the versatility of the catalyst. Both lignin-derived monomers and various dimers with different linkages were almost completely converted to cycloalkanes. Several characterizations were conducted to explore the fundamentals. The in situ formation of iridium, metallic iridium species is likely in charge of hydrogenation reaction, while rhenium oxide is difficult to be reduced at the reaction temperature of 260 degrees C. Now, bimetallic catalysts have no reduction temperature than both monometallic catalysts, providing a direct evidence of the synergistic interaction between iridium and the rhenium species that favors the hydrogenation reaction. Such a point has also been proved by XPS and XNS spectrals. Then the direct deconstruction of real lignin to lefsens was investigated. The carbon yield of the lefsens could reach up to 44 WT%, although the iridium modified rhenium oxide catalyst. The data is similar to the best in literature. The HSQC NMR shows clear that the aromatic ring signals disappeared after reaction, while the signals of hydrocarbon remarkably increased in comparison with that of the corresponding lignin. Thus, we demonstrated a promising system for the one-port production of leptins from lignin. Now, last, I would like to summarize my presentation. In this work, in this talk, I shows a potential for the conversion of lignin into different chemicals and fuels through designed catalytic route with different functional catalysts. We aim to convert lignin in a selective way. We try to meet the green and suitable catalyst chemistry concept as pursued by ChemSusChem journal. We acknowledge that lignin is a notorious complicated material in structure. Such a structure property causes a huge task for us to conduct our selective transformation. For future work, we may focus on new characterization technology, robust multifunctional catalyst, novel routes, efficient pretreatment and separation methods, one-port conversion, as well as thermodynamic studies. At last, I would thank my group leader, Professor Tao Zhang and Aiqing Wang for their help. I would also want to thank the collaborators from all over the world, for example, such as Professor Jianliang Xiu and Westwood in UK, George Hube in America, and the local collaborators in China. And this picture shows our subgroup members. Most of the work was finished by Dr. Bo Zhang, Dr. Hei Guo, Dr. Ms. Xinxin Li, and Yuxian Liu. Thank you for your attention. And I finished the presentation.
Okay, thank you a lot, Changzhi Li, for a very impressive talk with a lot of results. And I guess you're almost starved because this started just before dinner time, and now it's far beyond dinner time for you. I have a question for you on the very, very impressive mild deoxygenation reaction that you ran. You performed it at 120 degrees. What was the pressure?
What was the pressure? The pressure is about 3 millipar, 3 MPa.
3 MPa. Okay.
Yeah.
Okay. Thank you. And then I have also another question for you. Could you just scrutinize and discuss a little bit? You showed a lot of different metals. You showed rhenium, and you showed cobalt, and you showed tungsten, and then you also showed iridium, and you showed rhodium. Could you discuss the choice of these two groups a little bit in terms of sustainability in your catalysis?
Yes, actually, for tungsten and rhodium catalyst, they have different valence, and the stability actually is somewhat a problem. So in future, we need to improve the stability, but the selectivity, because it's moderate hydrogenation ability, the selectivity might be a good choice for our catalysis. So, but to improve this, another case for the improve the stability, I think some noble matter catalyst maybe is more suitable for the long-term reaction.
Mm-hmm.
Yeah.
Because I would consider like rhenium, cobalt, and tungsten, they are very sustainable. I mean, even though rhenium is far down in the periodic table, it's still very abundant. This is one of the metals that there's a lot of. But if you would go to iridium, for example, or rhodium, there's very, very little of that. And it's considered like a scarce source of metal. So I would maybe more consider that rhenium, cobalt, and tungsten would be good for these more raw transformations, and then maybe these more rare metals, they could be used in, for example, the hydrodeoxygenation when you have clean streams. Or what do you say?
I'm absolutely agree with you that we need to use some cheap materials for the catalysis, and also we I think in future maybe can you I don't catch your meaning for could you please say it again?
So I mean, you showed two different types of reactions, I would say. One pretty raw, like going from biomass or lignin down to the building blocks. And then you showed also other transformations, going from building blocks more to platform chemicals. And you used also more rare metals and then more abundant metals. So my more a comment is that maybe the rhenium and tungsten that you also showed for the catalytic fractionations is more appropriate. And then when you use, for example, iridium that you dope the rhenium with, or rhodium even, that is more for upgrading of pretty pure streams. Or what would you say there?
You mean how can I pre-treatment my lignin using?
No, actually not. I can maybe chat with you, and you can read the chat. There is one question, and that is, what is the extent of the deoxygenation in your experiments? I think it's a pretty broad question, because you show both deoxygenation and where you go all the way to alkyne.
Deoxygenation, the extent for motor compound, actually almost all the substrate can be converted. At least usually the yield of the alkanes would be higher than 80%. And for the deoxygenation of the real lignin, in this paper, we can from HSQC we can show clear that the major aromatic unit signals has been disappeared, and the alkene signals become increased. So the detailed deoxygenation extent is about 80%, and another work in this cobalt, the mobillium sulfide catalyst, the deoxygenation is for motor compound, the extent is over 95%, and for real lignin oil, we don't for this reaction we didn't perform the direct deoxygenation of lignin. This is a two-step strategy. So for the deoxygenation of the oil, the extent, we also calculated the extent is over 90%. You also he also can see our published paper. It has the detail date. I forgot it, the detail date, but it's over 90%.
Okay, there's also another question by Wayne Chia, and that is, how much of the lignin ends up at char in your reactions?
Eunice, how much lignin in the char? What?
Yes. Do you get any char formation?
Char formation. In the reaction, for tungsten carbide hydrogenolysis reaction, the charge actually is very significant. So the recycle of the catalyst is somewhat a problem. But for most of the reactions using lignin as a reactant, the charge formation is inevitable. But yes, we need to still avoid this. Maybe we can increase the hydrogenation ability. Yes.
Yeah. Okay, thank you. And you also have some more questions in the chat, and I hope that you have time to linger and answer these. Before I say goodbye to you, Changzhi, I would like to ask you to give my best to Feng-Wan at your institute.
Okay, thank you. I will translate your words to Feng-Wan. Thank you so much.
Thank you.
Okay.
Okay, then I just want to thank all of the presenters here today. I think it's been an excellent 4 talks. I also want to thank the audience for the seminar discussions that also were very inspiring. And again, I want to thank the editors of ChemSus for setting up this symposium and being able to cherry pick these 4 really, really nice talks. I give back the word to Andrea.
Yes. Well, this has been a great first virtual symposium for us, and I hope for all of you as well, with very exciting presentations. And I'd like to take this opportunity to thank our wonderful speakers, Katalin, Eric, Claudia, and Changzhi, for sharing their experiences with lignin valorization. It's been an absolute honor and a real pleasure to have all of you here today. A very special thank you goes out to Joseph. You've done a fantastic job as moderator, and we were very lucky to have you as part of this symposium, so thank you very much. Finally, thank you all very much for attending today, and if you're interested, you can find recordings and more information on upcoming symposia from our sister journals on the Chemistry Europe website under events. Also, if you want more research on lignin valorization in general, you're welcome to take a look through our recent special issue, which is available on the ChemSusChem website. So this is it for now. From all of us at ChemSusChem, thank you for your time and have a lovely rest of the day.